Good day, everyone. I am Kyle Emmanuel Ofrias, and today we're going to be solving some physics problems from Chapter 23, Electric Potential, Problems 23.1, 23.49, and 23.59. So for this problem, a point charge Q1 is equals to 2.10 times 10 raised to negative 6 coulombs is held stationary at the origin. A second charge Q2 is equal to negative 4.6 times 10 raised to negative 6 coulombs moves from the point X, which is equal to 0.15 meters, and Y is equal to 0, to the point X is equal to 0.25 meters, while Y is equals to 0.27 meters. How much work is done by the electric force on Q2? So, first of all, we're asked to find the work done by the electric force on the second charge. So, we're gonna use the electric potential energy of two-point charges formula, which is, as you can see at the top right, U is equals to 1 over 4 pi epsilon naught times Q times the second charge over the distance between them. And in order to get R, we're gonna just subtract the x components, which is 0.25 minus 0.15, and then you just put it in the Pythagorean theorem, which in order to get the magnitude of the distance, and you're gonna get 0.258, and you just substitute, and you're gonna get negative 0.337 joules. Second problem. A gold nucleus has a radius of 7.3 times 10 raised to negative 15 meters and a charge of plus 79 E. Through what voltage must an alpha particle with charge plus 2e be accelerated so that it has just enough energy to reach a distance of 2.0 times 10 raised to negative 14 meters from the surface of a gold nucleus? Assume that the gold nucleus remains stationary and it is treated as a point charge. So we were asked to find the voltage an alpha particle with a charge plus 2e needs to accelerate so that it has just enough energy to reach a distance of 2.0 times 10 raised to negative 14 meters. As usual, we're going to be using the electric potential energy of two-point charges, but in addition to that, we're gonna divide it by Q in order to get the voltage. So you just divide the entire formula by Q, and then you're gonna get U over Q equal to 1 over 4 pi epsilon naught times the two charges over R times to 1 over Q, and as you can see, you can cancel the small q's, and then you just substitute the given values in the formula, and then you will get 4.2 times 10 raised to 6 volts. Last problem. A small sphere with a mass of 2.5 grams hangs by a thread between two very large parallel vertical plates 5 centimeters apart. The plates are insulating and have uniform surface charge densities plus sigma or positive sigma and negative sigma. The charge on the sphere is Q equal to 7.10 times 10 raised to negative 6 coulombs. So what is the potential difference between the plates that will cause the thread to assume an angle of 30 degrees with the vertical? So we were asked to find the potential difference between the plates that will cause the thread to assume an angle of 13 degrees with the vertical. So we're going to use the potential difference formula, which is V is equal to ED. And in order to find E, we're going to use the force formula, which is F is equal to E, or the electric field, times Q, which is the charge. And then we're just gonna use algebra in order to get E is equal to F divided by Q, and then just substitute it to the potential difference formula, and then you're gonna get V is equal to F times T over Q. In order to get the magnitude of the force, we're gonna divide it first by the two components, the X and Y component, and for the X component, we're gonna get the tension times cos 30 which is equal to mass times gravity. And for the y component, we're gonna multiply the tension by sin 30, which is equal to the force. So you just divide both of the formulas in order to get F is over F over mg, which is equal to tan 30. And then you just use algebra, which will equal to the force is equal to F is equals to tan 30 mg. And then you just substitute the given values in the formula, and you're gonna get 0.014. And then you just substitute that value from the earlier formula, which we derived earlier, to get 99.6 volts. Thank you for watching, and God bless you. Pause.